Start recording. Yep, you're recording. Okay. All right, Dave. We're very happy to have Dave Offner from Carnegie Mellon University. I know Dave from many years back, and it's harder to get him here because he's in Pittsburgh. But now, because of the Zoom online environment, he's able to come. So this is joint work with a couple of authors. He'll tell us about it right now. Thank you, Dave. Go ahead. Take it away.
Great. Thanks a lot. Great. Thank you all for virtually coming, and thanks to the organizers for inviting me to speak. Right, so today I'm going to talk about a couple packing and decomposition problems on hypercube graphs. And right, so the first half I'll talk about, they all have the same flavor. Basically, what we want to do is take some fixed subgraph and see how densely we can pack copies of it into a hypercube. So in the first part, I'll talk about vertex and edge packings. And then in the second half, I'll talk about decompositions, where we'll want to ask which subgraphs can we perfectly partition the vertex set or edge set of a hypercube into copies of that fixed subgraph. Okay. Good. Okay, so let me sort of review some of the notation and basic facts about hypercubes that we'll need. So there's a hypercube for each natural number n, the vertices of Qn, right? So we denote a hypercube by Qn. The vertices of Qn are vectors with n coordinates, each of which is 0 or 1, and we put an edge between them if those vectors differ in exactly one coordinate. So here's Q1 has 2 vertices and 1 edge, Q2 has 4 vertices and 2 edges, Q3 has 8 vertices and 12 edges, etc. I think here's Q4. Good, so you've seen those before. There's lots of nice things we can make undergraduates count about hypercubes, right? So the number of vertices, how many binary vectors are there with n coordinates is 2 to the n, right? The degree of each vertex, right? There are n coordinates, so each vertex will have n neighbors, depending, right, there we can flip one of n bits, and if we multiply these numbers, n times 2 to the n, we'll count each edge twice, so the number of edges in an n-dimensional hypercube is n times 2 to the n minus 1. Okay, so all of these facts are going to be useful later. Okay, so we can define hypercubes explicitly, as we just did, or we can sort of build them recursively using the Cartesian product operation on graphs. And so just to, again, review some notation and vocabulary for that, let me use as an example of a Cartesian product, here, a Cartesian product between K2, or which is the same as Q1, and a path of length 3. Okay, so when I take a Cartesian product of 2 graphs, right, the vertex set of the Cartesian product is a set of ordered pairs where the first entry is a vertex from one of the graphs and the second entry is a vertex from the other graph. Okay, so here in this Cartesian product, since K2 has 2 vertices and P3 has 3 vertices, we get 6 vertices, okay, and we put an edge between them if they differ in one or the other coordinate, okay? And so when we do that, if they differ in, what are they differing in here? The second coordinate, right, we get 2 what we'll call horizontal copies of P3, one for each vertex in K2, and we get 3 what we'll call vertical copies of K2, one for each vertex in P3, okay? And so, you know, for any 2 graphs, we can take some Cartesian product like this. So just as a second example, if we took K2 with P3, sorry, with K13, we would get this Cartesian product. Good. Okay, and so as I mentioned, hypercubes can be constructed by taking Cartesian products. So Q1 is K2, and inductively the n-dimensional hypercube is the n-1 dimensional hypercube Cartesian product with K2. So Q2 can be thought of as right, 2 horizontal copies of K2 and 2 vertical ones. Similarly, to get Q3, I take 2 horizontal copies of Q2 and 4 vertical copies of K2 or Q1, etc. Okay, and so in general, you can think of Qn as the n-fold Cartesian product of K2, And one nice thing about this is depending where you put your parentheses, right, it means we can think of a large hypercube as a Cartesian product of smaller hypercubes in multiple ways, right? So for example, Q4 is the Cartesian product of Q3 and Q1. So here's two vertical copies of Q3 with 8 horizontal copies of Q1. But we can also think, right, that combine to make Q4. But we can also think of Q4 as the Cartesian product of Q2 with itself, right? So here's 4 vertical copies of Q2 and 4 horizontal copies of Q2 that make up a Q4, right? And so in general, I don't think I wrote it here, but right, Qn plus m is the Cartesian product of Qn and Qm, right? Okay, so now with that background on hypercube graphs, we can talk about our packing problems. Good. Okay, so the first problem we want to talk about is vertex packing, right? So the game here is we want to take a graph G. It's a fixed finite graph. It needs to be a subgraph of the hypercube, and we want to see how densely can I pack copies of G into the hypercube so that all the copies are vertex disjoint. Okay, so in Q2, clearly we can pack 1 copy in. We've used 3 out of 4 vertices. Okay, for Q4, I can take this G and I can pack 4 copies and then actually a 5th there, so I can pack. I can cover 15 out of 16 vertices in Q4 with copies of this graph G. Okay, so what are the questions? So the parameter we want to keep track of is this V of G comma N is the maximum vertex packing density of G in Qn, right? And what we're really interested in is as N gets large, this density is monotonic. What is the limit of this vertex density? And in 1990, Quentin Stout proved that for all cubical G, V of G is 1. And cubical just means G is a subgraph of Qn, right? So if I try to pack triangles in the hypercube, I'm going to fail because the hypercube is bipartite. So, but as long as G is a subgraph of some hypercube, if I make N large enough, I can pack with density as close to 1 as I wish. Okay, and the proof of this is quite nice, right? Basically, it's an inductive argument where we start with any packing we want, and then we successively augment that packing to get better and better packings for larger and larger hypercubes. So as an example here, I'll use the same G we used before, right? I said, okay, previously we had established that V of G2 is 3/4, okay? And so what I do is I think of Q4, right, as Q2 Cartesian product with Q2, and since I've got a 3/4 packing of Q2, I just look at all the vertical copies of Q2 and Q4, and I copy that packing into those 4 vertical copies, okay? And then since one of the vertices in each of those vertical copies was uncovered, I will have a horizontal copy that's empty, and so I can augment my packing, right? Okay, so once I've copied my packing into the vertical copies, I've achieved the same density, and then I can augment using a horizontal copy. So I will get the same density, 3/4 from the vertical copies, plus for the remaining vertices, I cover 3/4 of those, and that's where I get 15/16. Okay, and so I'm not going to draw it, but the next thing we would do is go to Q6, copy this Q4 packing into the 4 copies of Q4 and Q6, and then augment again. Okay, and so in general, you get this, right? So if you have some packing with density R in QD, right, the way the induction goes, then when you go to Q2D, right, you take QD Cartesian product with itself, you copy your packing with density R, and then get this 1 minus R times R additional factor, okay? And then next you would go to 3D, and you would have the previous density plus again some additional factor, and when you do the bookkeeping for how much you're being able to augment by, you get this nice geometric series, Okay, that again is a nice undergraduate exercise to see that it adds to 1. Okay, so no matter what packing we start with, I can augment it as n gets larger and achieve vertex density 1. Okay, good. Okay, so that's the story for vertex packing. What about edge packing? So edge packing is the same question except for edges. So here's a K13 copy of G, and I want to ask now, for example, how densely can I pack copies of G into Qn, into a hypercube, so that the copies are all edge disjoint. So for example, here on the right, I've packed 4 copies of this claw into Q3. There's a black copy, a blue copy, a green copy, and a red copy, and even though they overlap on vertices, they're edge disjoint, right? And so we can define the corresponding parameters for edges that we did for vertices, right? E of Gn is the maximum edge packing density of G and Qn, right? What proportion of the edges of Qn can I cover by edge disjoint copies of G? And again, we're interested in, as n gets large, what do these densities approach? And I will point out that edge, unlike vertex, unlike V of Gn, E of Gn is not monotonic, but you can still prove this limit exists. Okay, and Stout in 1990 actually proved that for some G's, E of G was 1, and conjectured that it was true for all cubical G's, but did not prove it. But okay, so I proved that in 2014, and the idea is the same. It's just a little trickier, but it's the same idea where we start with any given packing, and then as n gets larger, we augment it. But we have to be a little more careful with the induction is a bit different. Okay, so let me just give you an example that shows what we're doing. So here's a path of length 3 that we'll use for G. Okay. Obviously, we can pack 1 copy of that into Q2 with edge density 3/4, right? Okay, so now if I want to think about Q4, I think about it as Q2 squared. And so I'll explain why I write Q2 squared instead of maybe Q2, Cartesian Q2 in a moment. But what I do is I sort of say, okay, if I think of Q4 as Q2 squared, then I have 4 vertical copies of Q2, and I can copy my edge packing into those. I have 4 horizontal copies of Q2. I copy my edge packing into those, and at this point I have achieved the same edge density for Q4 as I did for Q2, right? 3 out of 4. Okay, and now I notice right down here in the lower right, I have one empty Q2. Okay, and it's not the same for vertices as right. So it's not the same as for vertices, right? I have these other edges that I just can't do anything about. But I do have this one lonely Q2 down there, so I am able to augment in the lower right and get a better edge packing for this graph. Okay, so the way this works is right. So for vertices, I went Q2, Q4, Q6, Q8. Here. Now, right, what I want is that, right, what the way this induction works is this empty edge here, I want that to turn into an empty Q2, right? And so in order, the next time, right, so in order to do that, I don't, here my induction will go Q2, Q4, Q8. I'll have to take powers of 2, not multiples of 2 for that to work. Okay, and you have to check that it works, but if you do, it does, and you'll be able to augment every time. You still need to check that these augmented packings, the density approaches 1. And so what you get is not a geometric series actually, but sort of an iterated function. So if I start off with a packing of QD with density R1, when I take QD squared, I get the same density as I had before, plus, okay, so it turns out this is the additional density I'm able to pack, and I call that R2, okay? And then when I take QD cubed, again, I start with density R2, right? I start with the density I had for QD squared, and then I'm able to add something to that, and it turns out you get this recurrence, right? The density for Q d to the I plus 1 is equal to the density for Q d to the I plus some additional factor, and so you're basically iterating this function given some fixed seed R1, or some, actually R1's not the seed, R1 is just a constant. You pick a seed, and then, well, I guess R1 is also the seed. Anyway, the good news about this is that this function has an attracting fixed point at 1 no matter what R1 is, and so when you write out the epsilons and deltas, you get that E of G is in fact equal to 1. Good. Okay, so that was, so for both vertex packings and edge packings, we can start with any packing, augment, and the densities eventually approach 1 no matter what fixed subgraph we have. Okay, so once we knew that, what were the remaining questions? First, I asked about some rates of convergence, right? If you look at these schemes, the vertex packings converge to density 1 much faster than the edge packings. And it's not at all obvious that these, we weren't careful to try to make them converge fast at all. We just wanted to know that they did converge, right? So I think a natural question is, what are the rates of convergence? And Gruslitz and Letzer in 2018 analyzed this for vertex packings, and they sort of gave a characterization of the optimal rate of convergence for vertex packing. And as far as I know, nobody has done this for edge packing, so I think that is still open. Okay, and then the second question at that time was which graphs can either vertex or edge decompose Qn, right? And here, again, decompose means a packing with density 1, okay? And so that's the subject of the second half of the talk. Okay, good. So we talked about vertex packing, we talked about edge packing, and now we want to talk about decomposing, right? Where we want to partition the vertices or edges of the hypercube into copies of our fixed subgraph. Okay, so for the vertex case, right, there's some sort of obvious necessary conditions for G to be able to decompose Qn, right? It's got to be a subgraph of a hypercube, and it's got the number of vertices in G has to be a power of 2, because the number of vertices in Qn is a power of 2, so if I'm going to partition a power of 2 into some vertices into some smaller sets, they all, right, the only thing that divides a power of 2 is a power of 2, right? And the question at that time was are these necessary conditions also sufficient? And in 2016, Gruslitz proved that they are, okay, at least if n is sufficiently large. So for sufficiently large n, he proved if G satisfies the necessary conditions, then it decomposes Qn, okay? And it's a beautiful result, but that's all I want to say about that. Good, because, right, so what I really want to talk about is edge decompositions, okay? So the question once we've done vertices is, can we do edges, right? And the question, so which subgraphs G decompose Qn? And again, when we sort of look at the combinatorics of edges, there are some obvious necessary conditions, right? First, G must be a subgraph of a hypercube, so it must be cubical. And then we have sort of two divisibility conditions, right? Overall edge divisibility, right? Qn has n times 2 to the n minus 1 edges. So if I want to partition the edges of Qn into edge-disjoint copies of some subgraph, right, that subgraph has, the number of edges in that subgraph has to divide n times 2 to the n minus 1. And then there's a third condition that I call degree divisibility, right? So we notice Qn is an n regular graph, right? Each vertex has degree n. So the degrees of G of my subgraph, which divide it, have to divide, no, it's have to be compatible with that, right? It's a GCD condition. Right? The GCD of the degrees of my subgraph have to divide n. Okay, and in 2016, Grusless, Leader, and Tan conjectured that if G satisfies these necessary conditions, then there exists N such that G decomposes Qn. Okay. And I'm about to tell you this is wrong, but it seems like it should be right, right? And so I want to sort of give some sympathy to this conjecture by saying the following, right? So for packing, it worked this way, right? You did the vertex case, and then the edge case was a little harder, but it all worked
Can I
out
ask a
fine.
question?
Yeah, go ahead.
On degree divisibility, is G regular? Because it might have different.
No, not necessarily. So
So by
G,
degree divisibility, I'm unclear what you mean on degree divisibility. Maybe.
yeah. So technically, what this I was sort of sweeping this under the rug, but the idea is that the GCD of the degrees of G divides n is the precise thing that has to be true.
Okay, thanks.
Yep. Yep. Thank you. Yeah, and please, anyone pipe up with questions or drop them in the chat if you have them. Good. Okay, so I was about to tell you, right? So for packing, right? We did the vertex case; it worked out fine. You did the edge case; it was a little harder, but it also worked out fine, right? And then for decompositions, you did the vertex case; it worked out fine. And of course, the edge case might be a little harder, but perhaps it should also work out just fine. But not only that, I think a lot of, to me, right, another reason why you thought, okay, this, why not? Why wouldn't this work out? Is this theorem of Wilson back in 1975, which is sort of one of the sort of seminal theorems about graph decompositions, was that sort of for the complete graph Kn, right? You have well, you don't have everything's a subgraph of a complete graph, right? But basically, if you have these edge divisibility conditions and degree divisibility conditions, anything that met those, right, you got the corresponding theorem for Kn. If it met the obvious necessary conditions, those were also sufficient if n is sufficiently large. Okay. So Grusless, Leader, and Tan made this conjecture, and which is sort of seems like it should be the next step in the story, but it's false. So Bonamy, Morrison, and Scott in 1917, and I was just talking about how we lost track of what year it is. 2017 came up with this counterexample, and you can generalize this counterexample, so it's a whole family of things. And what is this monster? This is Q5 minus 5 carefully chosen edges, right? So if I take Q5 and I delete the red edges, that's going to be a counterexample, and I can show you briefly why. Okay, so to show you why, I have to go back to undergraduate discrete math and count one more thing about the hypercube, right? So the hypercube, we know how many vertices, the degree of each vertex, the number of edges, but there's something else we can say is that sort of if you look at the hypercube I've drawn here on the left, the Q3, I've drawn 4 edges in each direction, right? 4 are horizontal, 4 are vertical, and 4 are kind of coming out at the board at us, right? And those directions correspond to the bit that is flipped between the two vertices, right? So the horizontal edges, what the horizontal ones flip the first bit, right? Right, the vertical ones flip the second bit, and the one coming in and out of the board at us flip the third bit, right? So we can call this the direction of an edge, right? Which bit is being flipped, and the number of edges in each direction is 2 to the n minus 1, right? There's 2 to the n, and there's n times 2 to the n minus 1 edges. and they're the symmetry among directions, so there must be 2 to the n minus 1 in each direction. Okay, so what did Bonamy, Morrison, and Scott do? They constructed this graph that has 2 to the 4th minus 1 edges in each direction, right? So Q5 would normally have 2 to the 4th edges in each direction, so they kill 1 in each direction. And then what you have to prove is the following, right? When you embed a subgraph into a hypercube, it might embed isometrically or not, right? So what do I mean by this? So if I embed Q2, which is a 4 cycle, into a larger subgraph, you can see if I embed this Q2 into some larger hypercube, the embedding will always have 2 edges in each direction, right? Whereas if I embed P3 into a hypercube, I can embed it with 1 edge in each of 3 directions, that's the top picture, or 2 edges in one direction and 1 edge in a second direction. That's the bottom picture, right? And so what they showed is that this graph is sort of rigid enough or dense enough that when you embed this into a larger hypercube, the edges that are in the same direction in this picture will always be in the same direction, okay? And since a larger hypercube, the number of edges in each direction is going to be some power of 2, and 2 to the 4th minus 1 doesn't divide that, right? This graph could satisfy the necessary conditions, but will never decompose a larger hypercube. Okay. And so the way I interpret this, right? So again, the big question we're thinking about is which subgraphs decompose Qn. Is we had these 3 necessary conditions from before, right? And now we add, I think, add a 4th one that there's got to be a direction divisibility condition that's met, right? So there are 2 to the n minus 1 edges in each direction, and whatever graph we're trying to embed has to be compatible with that. Okay, and so the obvious big open question is, right, is the same as the GLT conjecture, right? Is if G satisfies these necessary conditions, are they sufficient? And as far as I know, no one has been courageous enough to actually conjecture that this is true, but right, if not, we'll just keep adding necessary conditions until it is, right? Good. Okay, so that's sort of the negative result. Let me tell you about some positive results for decomposing Qn, right? And so you'll see this is really wide open. Even for paths, there are still, what are the simplest subgraphs we can try to decompose a hypercube into, right? Paths maybe are the simplest. And even for paths, it's quite, we still don't know everything. Okay, so let me tell you what we do know. So in 2015, Erdi and independently Anik and Ramras proved this theorem for odd hypercubes. So if n is odd, let me go back to red here because it's a bit more visible, and I have a path of length k that satisfies the necessary conditions, okay? And here, since a path has a degree, well, anyway, let me just, and pk satisfies the necessary conditions, then it decomposes the hypercube, okay? And Erdi conjectured that the same would be true for even hypercubes, right? So if n was even and the path length is compatible with the number of edges in the hypercube, then it would decompose the hypercube. Okay, and sort of silly me, I thought, okay, well, if they did the even case, well, what could be so hard about the odd case? So let me do a couple calculations that show you, sorry, the opposite, that the even case is significantly harder than the odd case. Okay, so for example, Q7 and Q6 are 7 and 6 are pretty close to each other. So let's see why the path problem for Q7 is easier than the path problem for Q6. Okay, so for Q7, we have 2 to the 7th vertices, 7 times 2 to the 6th edges, and each vertex has degree 7. Okay, and the key now is that 7 is odd, right? So if I'm going to decompose a hypercube into paths, right? And each vertex has degree 7, right? If a vertex is on the interior of a path, right, that path is going to contribute 2 edges to the degree of that vertex, right? And so The fact that we have odd degree vertices means that every vertex has to be the endpoint of at least one path in the decomposition, right? Because okay, so there must be at least 2 to the 6th paths, right? There are 2 to the 6 vertices, or sorry, there are 2 to the 7th vertices, so if I pair them up, I get at least 2 to the 6th paths. So how long could they be, right? I take the number of edges, 7 times 2 to the 6th, divided by the number of paths, right? They could be at most 7 edges long, okay? So in these odd hypercubes, you can't have a decomposition into long paths because every vertex has to be the endpoint of some path. Okay, and so the possible path lengths, right, the number of edges have to divide the number of edges in Q7, right? For Q7, I only have 4 possible path lengths to worry about. Right. On the other hand, for Q6, I do the same calculation, right? I have 2 to the 6th vertices, 6 times 2 to the 5th edges, each with degree 6. 6 is even, so we don't have this endpoint constraint. Okay, so the only constraint on the path lengths is that it must divide 6 times 2 to the 5th, so we get a whole lot more paths we need to worry about, including much longer ones. Okay, so this is why the even case is much harder than the odd case. Just to give another example to be very concrete here. So, right, so for Q35, I only have to worry about path lengths up to 35, whereas for Q30, there are many, on the order of, right, there's over 100 paths I need to worry about. Some are quite long. Okay. Okay, so this is sort of the first glimpse into why the even case is harder. Okay. There's also been work on decomposing into cycles, and this is actually our strategy for decomposing into paths. But so let me just tell you about what's known about cycles. So back in '55, Ringel proved, so there's a lot of work on Hamiltonian decompositions, right? Decompositions into Hamiltonian cycles. And in '55, Ringel proved that, sorry, I can just make this bigger, right? So for hypercubes Q2 to the n, right? So Q2, Q4, Q8, Q16, those all have Hamiltonian decompositions, and he conjectured that this should be true of all hypercubes, and that was proved in 1982 by Aubert and Schneider. Okay, and there's also been some work with short cycles, Mollard and Ramres in 2015, and Tapadia, Wapner, and Bors more recently. Good. And so, as I said, our goal initially was to think about Airy's conjecture, right? Think about path decompositions, but our strategy is going to be to decompose a hypercube into long cycles, okay, and then cut those cycles into shorter paths, all of the same length. And if we can do that, then we've got a path decomposition, right? Okay, so this theorem is, I don't even like the way I said it, but the point is that for any sort of factor of n, we can get, right, a cycle decomposition of Qn on the order of length 2 to the n over n. Okay, so let me show you how this is an improvement over prior knowledge. Okay, so let's think about this in terms of progress towards Airy's conjecture. So I take a cycle, I chop it into 2 or more paths, and so progress towards Airy's conjecture can be summed up sort of in the following strategies, right? Let's take a theorem. If K is at most blah, and a path satisfies the necessary conditions, then PK decomposes Qn, right? And so the goal here for Airy's conjecture is to sort of, right, is the longest that question mark could be is 2 to the n, right? And so the question is how well are we doing? So Horak, Siran, and Wallace already in '96 showed that if I have a path length up to length n, those path lengths can decompose the hypercube. The Mollard and Ramres result, remember, short cycles gave us up to 2n. Tapadia, Wapner, and Bors give us up to about n squared, and our result gives us up to about 2 to the n over n, right? So we're still not there. Airy's conjecture is still open, but we're sort of closer than we were before. Okay. Good. Okay, so let me give you some insight into how we decompose a large or hypercubes into long cycles that are long relative to their number of vertices. Okay, and the paper got surprisingly technical, but I think I'll describe some of the ingredients and then and then and that'll be about as much as we can do. Okay, so what I want to do is draw, so here I have a cycle, C6, and what I want to do when I want to think about it, the Cartesian product of cycles, is I want to draw it sort of in this vertical representation where I think of the top half edge and the bottom half edge on the screen as connecting, right? And so if I do this, then I can represent a Cartesian product of cycles. So for example, I have C6 on the left here and C8 up here. I can sort of draw it this way, where I have the black edges on the left connecting to the black edges on the right, and the red edges on top connecting to the red edges on the bottom. Okay, I call this a torus because, right, if we actually connect those, I can embed it on the surface of a torus. Okay, and so what I'll show is that we can decompose tori into cycles. Okay, and that's going to be the key step in decomposing hypercubes into cycles. Okay, so for Q2, Q2 itself is a cycle. There's only one cycle decomposition. It's a cycle of length 4, so there's really nothing to say. Okay, Q4 we said is the Cartesian product of Q2 with itself. Okay, so so what do we do here? We take Q2, we take the Cartesian product with Q2, right? And you can find the address of any vertex by just concatenating the address of the right. This is sort of 1, 1 on the left and 1, 0 on the bottom, right? We don't put the comma in typically, right? We just say this is address 1, 1, 1, 0. Okay, so this Q4 is actually a torus. It's a Cartesian product of 2 cycles. Okay, and so what cycle decompositions does it have, right? I can just take the 4 horizontal C4s and the 4 vertical C4s, and I can decompose Q4 into 8 C4s, right? I can also sort of I can divide it into 4 C8s using sort of the following strategy. I sort of take 4 strands, so I have a red C8, a black C8, a blue C8, and a green C8, okay, by sort of, instead of going straight over or straight up, going alternating up and over, okay. And I can also decompose Q4 into 2 C16s, right? So this is the Hamiltonian decomposition of Q4, and I call this sort of a wiggle, right? Where if I start in the lower left, I go sort of up, I wiggle up and down until I get to the end of a row, at which point I go up to the next row, I wiggle up and down until I go up and come back to where I started. So I have a red C16 and a black C16 there. Okay, and so this is sort of the inspiration for what we're going to do going forward, right? Is that given a torus, given a Cartesian product of 2 cycles, I can decompose it into cycles of the same length using what we'll call the wiggle decomposition. So a 2 wiggle divides it into 2 cycles. Okay, and here I'll just isolate the red cycle here, and you can, and the cycles have to satisfy, right? The cycles in this case both have to have even length for the 2 wiggle to work. But I get a red cycle and a black cycle when I do a 2 wiggle. If I have different divisibility conditions, I might be able to do a 3 wiggle. So here I have a red, blue, and black cycle. Here I'm isolating the red cycle. And now I'm showing you all 3 cycles again. Okay. And just to make sure, you have to go back to the eye doctor, right? There's a 4 wiggle. Again, as long as certain divisibility conditions are satisfied, I can divide into 4 cycles, etc. Right. Okay. So this gives us our sort of high-level strategy for decomposing Qn into cycles. Right? Start with a hypercube, and instead of going directly to cycles, first decompose into toruses, or tori, and then once I have tori, use my wiggle decompositions to decompose those into cycles. Okay, so to put a little more meat on those bones, right, the idea is to write our hypercube Qn as a Cartesian product of some smaller hypercubes. then inductively, we know that those smaller hypercubes are going to have some cycle decompositions. Okay. I'm going to use those cycle decomposition to decompose Qn into tori, and where it gets complicated is this isn't always possible. So sometimes I'll have to decompose them into quote-unquote tori, which are torus-like objects, but unfortunately not honest-to-goodness toruses, and that's what we'll have to see. That's where things get technical. Okay, but then once I've decomposed Qn into tori or tori, then we'll use the wiggles to decompose the tori into cycles. Okay, so here are some examples. The example we looked at, right, so we took Q4, we thought of it as the Cartesian product of Q2s, right? Those Q2s each have a cycle decomposition, C4 Cartesian with C4, that gave us one torus, and that torus could be decomposed into two C16s or four C8s or eight C4s, okay? So for Q6, what's the next one? We're going to think of Q6 as a Cartesian with Q4 and Q2. Then Q4 decomposes, for example, as two C16s. Q2 decomposes as C4, and so I get I'm going to get two torus-like objects out of that, and those I can decompose into, for example, 4 cycles of length 48 or 8 cycles of length 24 or what have you. And then we can keep playing this game. We can decompose Q8. The powers of 2 are nice, so for Q8, for powers of 2, I get honest-to-goodness toruses, and things work out nicely. But then for Q14, right, I get Q8 Cartesian with Q6, I get 8 torus-like objects. Okay, and so I think I have just enough time to give you an indication of sort of to show you how it gets a bit complicated, but that we can deal with it. So to sort of see the complexity, let's look at Q6. Okay, so Q6 is, we said, the Cartesian product of Q4 and Q2. Okay, and Q4 decomposes as two C16s. Okay, so here I've drawn the two C16s that decompose Q4. Notice even though these cycles look the same, the vertices come in different orders, right? So here I have all the edges of Q4 divided into 2 cycles. Okay. So now I might think naively, okay, let's take the Cartesian product with C4, right? So so we would get 2 toruses. What's the problem here? So I get all the vertical edges exactly once, right? Because the vertical cycles are different. But the horizontal cycles, I get every edge exactly twice, right? So you can check that this red edge down here, right, this vertex is the all zeros vertex, and this vertex is the all zeros vertex with a 1 at the end. Okay, and that's the same edge I get over here. Or for example, just to take this green edge here, you can check that that green edge is found over here in my left torus and over here in my right torus. Okay, so what's the issue is I can decompose these toruses into cycles, but I'm going to get every horizontal edge twice. It's not going to be a decomposition. Okay, so what do? I say, okay, I only want every horizontal cycle once. So here it's not so bad. The Q4 is bipartite. So I say, let's only take the each horizontal cycle once, right? So I pick eight vertices in the left cycle and 8 vertices in the right cycle and say, let's only take the horizontal cycles there, okay? And if I take those, right, so these are what I call tori, or more formally, right, these are just sort of subdivided toruses, right? So if I take these 2 subdivided toruses, right, if I partition the vertices of Q4 into 2 sets and only take the horizontal cycles once, okay, then I get these 2 subdivided toruses that are nice and symmetrical, so I can still do my wiggle decomposition and break each torus into 2 cycles, and since I've done it nice and symmetrically, those cycles are all the same, and I get a decomposition into 4 cycles of length 48 or whatever that is. Okay, so there's a lot of bookkeeping to keep track of in terms of as you get into higher dimensions, how do you find how do you make sure that every edge is being counted once, and how do you make sure that the subdivisions in your toruses are compatible with these wiggle decompositions all having cycles of the same length? Okay, but all right, if you wanna torture yourself with that, then you can read the paper, but okay, but here's some numerical examples that show that we get, sort of almost all the paths for small examples, but still not all the paths that we would want for Erdes conjecture. Okay, so let me wrap up by saying, right, so what we do understand, we understand vertex packing, we understand edge packing, although we still no one's analyzed the rates of convergence for edge packing, so that's still open. We understand vertex decomposition, and we still understand a little bit of edge decomposition, but there's a lot more to understand. And what's still open is even paths and cycles are still open. Erdes conjecture is still open. Edge decompositions of QN more generally is wide open. And in thinking about this stuff, I learned that there's also a lot of research on sort of decompositions of Cartesian products in general, and there's a lot known there, but there's also a lot that people don't know. For example, there's a conjecture that if you take two graphs, that each of which has a Hamiltonian decomposition, then their Cartesian product has a Hamiltonian decomposition, and this is known for many, many graphs, but still not for all of them. So there's a whole other direction to take this as well. But okay, I think my time is up. So thank you for coming, and I'll be happy to take questions.
Thank you. Actually, we have 10 more minutes, but you can, if you have anything more to say, you could. But we can also
I think I've yammered at you enough.
Okay.
I could take you down many further rabbit holes, but maybe it's a good time to take questions.
Okay, good. We get plenty of time for questions. So we're a questioning crowd. So let's open the floor for questions.
David, I have one. So can you put the sort of grand